In the first segment, we learned about pseudo-random number generation, and we also learned the base R function sample. Now we're going to learn a series of additional functions that are very convenient for working with random variables in R. So base R has actually lots of functions for common random variables. Each random variable has an abbreviation, for example, norm for normal, and then each of these abbreviations has 4 functions that are constructed by placing a single letter in front of it. So if we put D in front of the abbreviation, we get the density for a continuous random variable, or mass function for a discrete random variable. If we put P for probability, we get the cumulative distribution function. If we put Q for quantile function, we get the inverse CDF if it's a continuous random variable, or the generalized inverse if it's discrete. And if we put R in front of it, we get a function that makes random draws. So I'm going to illustrate each of these for the normal random variable. The relevant commands are called dnorm, pnorm, qnorm, and rnorm. But before I do that, let me just point out to you many of the other built-in random variables in R. We've got beta, binomial, Cauchy, Poisson, student t, uniform. There are lots of possibilities here, and they all follow the same naming convention. So on this slide, I show the short abbreviation for each of the distributions, and then, of course, you've got a D, a P, a Q, and an R function for each. If you need to use a random variable that is not on this list, that's okay. There is a task view that you can click on here to view lots of packages in R that can be used to look at more exotic kinds of random variables. But for now, let's go back and take a closer look at the normal random variable. So the first thing to know about the normal random variable in R is that R parameterizes it in terms of the mean and standard deviation. So many textbooks parameterize it in terms of the variance, but R parameterizes it in terms of the standard deviation. So I'm going to be showing you how to make a plot of the normal density. Before I walk through the code, let me just show you the result of running it, which appears on the next slide. Here's your familiar bell curve. So we're plotting the standard normal density between -4 and 4. So how does this work? Well, the first thing that I'm going to do is I'm going to define the mean and the standard deviation of this distribution in lines 2 and 3 of the code block. Then I'm going to construct a tibble that contains the x-coordinates. To do that, I'm using the function seq to generate a sequence, so a numeric vector that ranges from -4 to 4 by increments of 0.01. Then I'm going to use the dplyr command mutate to add another column to this tibble. So I started out with just the column x. Now I'm adding a new column, which I'll call density. And that is the standard normal density, dnorm, evaluated at the points x. So you can see that those mu and sigma parameters were already set above in lines 2 and 3. Now that I've got this tibble, which is 2 columns, one is x and one is the density at that particular x location, I can use ggplot to make the plot. Here I'm just using geom line. And if you'll notice in line 9, where I pass in the aesthetic mapping, I don't actually specify x equals x, y equals density. It's perfectly fine to just leave those arguments unnamed. The first one will always be the x-coordinate of the plot. The second one will be the y-coordinate if you don't tell R otherwise. And indeed, that produces exactly the bell-shaped curve that we're familiar with. The next thing I'm going to do is the standard normal CDF. So the code here is almost identical. The only thing that's changed is in line 5, I've replaced dnorm with pnorm. Remember, P stands for probability, so pnorm is the normal CDF. And I've just named that column, the second column of my tibble, which is set up in lines 4 and 5, CDF. So lines 4 and 5 of the code block are going to create a tibble with 2 columns. One is x, and the other one is the CDF evaluated at that point x. I'm still using exactly the same sequence from -4 to 4 by increments of 0.01, and I'm still using ggplot to produce a geom line, and here it is. I can also make some standard normal draws. So to do that, I will use the command rnorm. So here I'm relying upon the definitions of mu and sigma from the previous code blocks. So remember, mu was set to 0 and sigma to 1. And now what I'm going to do is I'm going to generate 500 draws from this distribution. So in line 2 of my code block, I have our norm of 500, comma, mu, comma, sigma. And what that does is generates 500 standard normal draws. Now, to illustrate those draws, rather than just printing them out to the screen, I'm again going to use ggplot. This time I'm using a histogram. And as you can see, we have a pretty good approximation to a bell-shaped curve, as we should. Now here's an example with a discrete random variable. So I've decided to choose the binomial random variable with n equals 10 and p equals 0.2. So I'm going to be using a very similar kind of template to what I used for the normal distribution. If you see in lines 4 and 5, I'm setting up a tibble. The main difference is here I'm setting up a tibble with the discrete values, the integer values from 0 to n, because those are the only points where the binomial distribution actually has positive probability. Those are the support points of this distribution. And then I'm going to create the column p, which gives the probability mass function. So I'm going to use the command dbinom. D stands for density, and in the case of a discrete random variable, this means mass function. So dbinom gives me the probability that a binomial random variable takes on particular values x. Again, I'm going to use ggplot to make the plot, but this one is a little bit more intricate. So here I'm going to use geom_point to plot a dot at each of the locations x and p from lines 4 and 5, where I set up my tibble. But then, because it's traditional to include a vertical line segment connecting the horizontal axis to those points when you're depicting a discrete random variable, I'm going to use a command that I don't believe we've met before in our examination of ggplot. It's called geom_segment. And what you can see it's doing here is it's specifying the endpoints of a line segment. And just to make things clear, I'm also going to add a title to my plot. So if you look at the next slide, you will see the result. I have points that represent the probabilities of each of the values on the x-axis, and then I have vertical lines connecting those to the horizontal axis. I can similarly plot the CDF of a binomial distribution. This one is going to replace in line 5 dbinom with pbinom. And it's going to replace in the ggplot, it's going to replace the geom_point with geom_line. And here we're going to get a kind of a stair-step pattern. But I want you to notice one more thing in line 4 of the code block. Here I am not choosing discrete values x, because remember that a cumulative distribution function is not just defined at points where the random variable has support. It's defined on the entire real line. So I'm instead going to use the function seq to plot a sequence of values that range from 0 to n+1 by increments of 0.01. And you can see the result here with this characteristic stair-step pattern. Every location where there's a step is a location where this binomial 10, 0.2 random variable has a support point. The CDF jumps at each of those locations. And I can similarly make a sequence of binomial draws. Here I chose to set the seed to an important historical date. And I'm using rbinom to make 500 draws from exactly the same binomial distribution that we've worked with before. Finally, I'm going to make a bar plot using geom_bar. And indeed, this seems to match up pretty well with the PMF that we plotted a couple of slides back. So that's the end of this segment. It was a very short segment on the normal random variable and the binomial random variable to help you see how to use the d, p, and r functions for each of these two random variables. And now it's your turn to play around with some additional random variables in R. Question 1 is going to ask you about the exponential random variable. Question 2 about the Poisson random variable. And question 3 is going to ask you to work with the quantile function of a normal random variable, which is something that you would need to do if you were computing a confidence interval. So where I write ME here, that stands for the margin of error. So the margin of error is going to be in the sort of for a 95% confidence interval, the margin of error will be 1.96 times the standard error. But here you're being asked for an 89% interval. So you'll need to use QNorm to figure out what to replace 1.96 with. And finally, you're going to make a little confidence interval of your own using some random draws from this normal distribution, and you're going to see whether they actually result in an interval that covers the true value of mu, the population mean.